Hello, myself Vipul Bajaj, and my topic for the presentation is virtual memory management in Linux. Before going deep into that, let's first talk about what is virtual memory. Virtual memory is a computer systems technique that enables a computer to use more memory than the physical RAM available in the system. It is a memory management technique that uses the hard drive space as an extension of the physical memory to temporarily store data that would otherwise be stored in RAM. This can be implemented using both hardware and software. The memory addresses used by program, which are called virtual addresses, are mapped into physical addresses in computer memory. Now let's talk about the way of working with virtual memory. Virtual memory works by dividing the computer's memory into fixed size blocks called pages. These pages are typically 4 KB in size, and the operating system uses a page table to keep track of which pages are currently in physical memory and which are stored on the hard drive. When a program tries to access a page that is not currently in physical memory, the operating system generates a page fault and swaps out a page of memory that is not currently being used to free up space for the requested page. This process is called page swapping, and it involves copying the page from the hard drive to physical memory and updating the page table to reflect the new location of the page. One huge benefit of using a virtual memory is that it optimizes a computer's performance by providing a larger address space for programs to work with than what is physically available in the computer's RAM. By doing so, it allows the computer to run more programs simultaneously and handle larger datasets without running out of memory. Virtual memory also helps to optimize the use of physical memory by allowing the operating system to manage the allocation of memory to different programs based on their current needs. Another way virtual memory can optimize a system is by providing memory protection. Each process running on the system has its own virtual address space, which means that it cannot accidentally overwrite another process memory or access memory that it should not be able to access. This protects the system from crashes or malicious attacks that could be caused by programs accessing memory they should not have access to. Now let's understand what is Linux operating system. It is an open source operating system created by Linus Torvalds in 1991 as an alternative to the Unix operating system. It is built on a modular architecture, which means that users can choose which components to install and which ones to leave out. This makes it possible to create a custom operating system that is tailored to the specific needs of the user or organization. Its key features are its flexibility and modularity, which allows it to be customized and tailored to meet specific needs. And the strength of Linux is its command line interface, which provides users with a powerful set of tools for managing the system and executing tasks. And here's the virtual memory management in Linux. It is based on the demand paging principle. Demand paging is a memory management technique used in operating system that only loads pages into physical memory when they are needed by a process. A process virtual memory space is divided into fixed size pages. When a process requests access to a page that is not currently in physical memory, a page fault occurs. The operating system responds to the page fault by loading the required page from disk into physical memory. The virtual memory management system in Linux consists of several components, which are first, address translation. It uses a page table to map virtual addresses used by a program to physical addresses in the memory. The page table is managed by the kernel and it is used to translate virtual addresses to physical addresses. The processor generates logical address, which is then translated into physical address by the memory management unit using some mechanism, uh, wi- and that physical address is then stored in the memory. Now the next component is page replacement. When physical memory becomes full, Linux uses page replacement algorithms to select pages to be swapped out to the disk. And the most commonly used algorithm is least recently used LRU algorithm. Suppose the reference string first asks for page 0. So initially all the frames are unallocated, so it will be allocated a frame in the main memory. Then it asks for 1, so it will also be allocated, and then it asks for 2, so it will also be allocated. Now all the frames are allocated and there is no space left in the main memory, and now the string asks for page 3. So as per the algorithm, the least recently used page is 0. So the page 0 will be swapped out to the disk, and page 3 will be allocated a frame in the main memory. And similarly, using this algorithm, we can allocate frames to the pages in the main memory for the further uh, string. Next, swapping. When a page is swapped out to the disk, it is stored in a special area on the hard drive, which is called the swap partition. Like when all the frames are allocated and there's no space left, and the new process comes, uh, one of the old processes swapped out to the swap partition, and the new process is allocated a frame in the main memory. Next, how is memory allocated on Linux? The most commonly used mechanism is the buddy allocation system, in which the total memory is divided into equal partitions of fixed size blocks until uh, the size of the block is just greater than the asked allocation size. Suppose we want to allocate a, a memory of 22 KB, so and our total memory is 128 KB. So 22 KB is just less than the 32 KB block. So 128 KB will first divided into 64 KB blocks, and then it will be again divided into 32 KB blocks with total 4 blocks, and that 22 KB is then allocated in one of the 4 blocks. Linux also uses a memory protection mechanism to protect programs from accessing memory that they should not be able to access. Each program has its own address space, and the kernel uses page table to enforce memory protection. Overall, the virtual memory management system in Linux is designed to be efficient and flexible, allowing programs to use more memory than is physically available in the system's RAM. By dynamically managing memory allocation, Linux is able to optimize the use of physical memory and provide a stable and reliable computing environment. Now let's talk about some of the techniques used by Linux for optimization. First is process scheduling. Linux uses a process scheduling algorithm to manage the execution of programs. The scheduling algorithm determines which process should be executed next based on priority, CPU usage, and other factors. The goal of it is to ensure that all processes receive a fair share of CPU time, and that high priority processes are given priority over low priority processes. Next is disk caching. Linux uses disk caching to improve disk performance. It involves keeping frequently accessed data in memory so that it can be quickly accessed by programs. One of the most commonly used techniques is read-ahead caching, which involves reading ahead a block of data from the disk into the cache before it is actually requested by a program. It helps to reduce the time required to access data from the disk, as the data is already in the cache when it is requested. Next is file system optimization. Linux uses journaling file systems such as ext4 and xfs, which help to ensure that file system data is consistent and reliable. It also uses various block allocation algorithms to optimize file system performance, such as the contiguous, linked, and index allocation algorithms. File system compression is another technique used by Linux to reduce the amount of disk space used by files which can improve overall system performance. And the last is network optimization. It is a crucial factor for improving system performance in Linux as it impacts network communication speed and reliability. Linux has several techniques to optimize network performance, such as TCP/IP tuning, network interface bonding, packet filtering and firewalls, and many more. Adjusting TCP/IP tuning parameters like MTU, congestion control algorithms, and buffer sizes can reduce packet loss, improve throughput, and decrease latency. But virtual memory also has some drawbacks. First, since it uses disk space as a supplement to RAM, it can slow down system performance if the disk is slow or heavily used. Secondly, since data has to be transferred between RAM and virtual memory, it can also lead to performance issues if the system is low on physical memory and has to frequently swap data in and out of virtual memory. So that was all about virtual memory management in Linux. Thank you.